Hello.
Good afternoon, Professor.
Good afternoon, Caroline. And good
Good
afternoon.
afternoon.
Oh, good afternoon. See, that was Savannah, but there was no green square. There's like a missing green square in the universe. But that was good afternoon, Savannah, and and I also totally saw Caitlin. Sorry. Good afternoon, Caitlin. Good afternoon, Kevin. Good afternoon, Amanda. Good afternoon, Mackenzie. Good afternoon, Adon. Good afternoon, Amy. Good afternoon, Stephen. Good afternoon, Samaya. Good afternoon, Erica. And someone just came but didn't come. Yes. Okay. Hold on. And good afternoon, my board, which is even worse than usual. Give me a second. The board is even. The board is forcing me to talk less and use the board more today. I mean, it's even more finicky than usual. If I leave it alone for a minute, it dies. So I'm going to go straight to it. We are in that stage of the year where we're really closing down on the point of we're getting to the point of why you've been slogging through all of this stuff for 2 semesters. Like, it actually is a story, a mathematical, physical, and historical story that actually, in my judgment, has a punchline, and we're trying to get to that punchline. Or I mean, it has a point, and we're getting to that point, and we will land on that point in our very last class, and we're getting very close to that. So I'm going to get, but I want to just remind you or warn you that from here on in, like, I still owe you stuff. Maybe some of you owe me stuff, but you don't. If you don't, but there's no new stuff besides the final, which will be taken at home during the finals week. We'll discuss that later in the next couple of classes. But my real issue is this, or my real advice is, you're not worried about computation anymore from here on out, really. From here on out, I want you to try your best to follow the concepts that I'm trying to lay down. If I do a calculation like today, it's for the purpose of showing you something. It's for the purpose of showing you how to derive a certain result, and it's because I think you need the result to put together and see the larger conceptual conclusion that we are now trying to get to. Long way of saying, don't think so much for the next 3 classes over how would I solve a really complicated numerical computation on this topic. Don't worry about that. It's not going to happen. The next 3 days, I'm putting together the concepts for you. And what you want to do is devote your attention to trying to follow the reasoning and the logic behind the concept. All right, that's enough of that. So I want to make sure to keep the board alive. So okay. So there goes the board. I knew it. Okay. All right, I'm not even going to try. Okay, I'm going to, oh no, it's there. It's there. Hang on 1 second. Okay. One thing I want you to write down, one big takeaway from the last 2 days. For the last 2 days, we've been talking a lot about electrostatic fields, and specifically, we've been talking about field lines. Field lines are a representation, but they're really very, very rich and important representation. They enable us to picture fields. Fields are very abstract. They're hard to picture. It's easier to picture what's going on with fields when we picture field lines. Remember again, so I'm going to tell you to write something down in a second, but remember again, the whole idea of a field, the whole idea is that when something is over here at this point in space, some thingy thing, like some amount of mass or some amount of charge, if there's some amount of stuff over here in space, then there is necessarily field everywhere else in space. The character of the field, the character, the details of the field over here in space are the information of what's going on over there in space. Specifically, the field, remember, field over here means the magnitude and the direction of the push or the pull waiting to happen here due to some stuff, some mass or some charge that's over there. The specific details of the field here are conveying or storing or transmitting the information, the specific details of the information describing what's going on over there. I'm going to say it one more time. Field over here is the information describing stuff that is over there. I mean, field is not stuff. Mass and charge are stuff, are thingy things, are particles. But whatever mass or charge is at any given point in space is known, is accessible, is accessible to any and all other points in space by virtue of the field conveyed throughout space. So the specific details of the field over here tells space the specific details of what is going on over there. And by specific details, I mean the magnitude and the location of the point charges or masses over there. Going to be now one level more specific. If there's a whole bunch of points of charge or mass over here, as realistically there usually are, if there's a huge collection of points and charges and masses over here, then the farther and farther away we are looking at them, the more and more big and macroscopic we as scientists, as researchers, as human beings are compared to these tiny, tiny bits of charge and mass, the more these collections of point charges start looking like continuous shapes of charge or mass over here, right? Like if you stand away from a planet, you don't see dot, 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 you see planet, right? If you stand in the lab near a ball of charge, you don't see electron, 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 you see ball of charge, sphere of charge, or maybe you see plate of charge, or maybe you see like wire, like line of charge, or maybe you see some very complicated shape that's assembled together from all these simpler, more elemental shapes like spheres and lines and plates. Ultimately, then what I'm saying is the magnitude and the direction of field over here is conveying the shape, the organization, the distribution of charge or mass over here in space. And the direction and magnitude of field over here is conveying where this in space, this distribution is. So I'm going to say one last time, even though I know you get this, many of you, I think, I'm going to say one last time, magnitude and field over here conveys distribution and location of charge or mass over there. We're right now talking about electrostatic fields. So E field magnet. So I'm going to say it again. Magnet. So please be writing this down somehow. Like I will get to my board in a minute and get to all the things I've already written down, but I want this to be clear in your mind. Magnitude and direction of E field over here conveys location and distribution of source charge over there in space. Lastly, now here comes the like sort of how do we imagine or picture this field information in our minds? How do we draw and represent these magnitudes and directions of fields on paper or on computer screens? We do it, of course, through field lines. So all these field line diagrams that we've been studying for the last few days, you notice they get pretty intricate pretty quickly. Like a field line diagram is sort of simple when you just have like one point of charge. Then as you start adding points of charge, as you have one over here and one over here, or two over here and one over here, or as they start getting a little bit more intricate, the field line diagrams get more and more intricate, right? More and more fancy, maybe more complicated looking. And remember, the field line pictures that we looked at the last 2 days, they only got as complicated as basically like a helium nucleus or something. I mean, they only got as complicated as like 3 positive points over here and like one negative point over here or something. You can imagine once we're really getting into like the field created by, a whole slew of molecules creating a material, like even just a hunk of metal or something like that. You can imagine the field line diagrams start getting very, very intricate. But here is my point. Oops, sorry. Here is my point. They're only as intricate, field line diagrams are only as intricate as the source distribution that creates them. Here's a sentence I really want you to write down, please, if you're still with me. Here's the sentence. The patterns in field line diagrams are only as asymmetric as the distribution of source charge which creates them. I'm going to say that again. The patterns in field line diagrams are only as asymmetric as the distribution of source charge which creates them. I'm going to say it one more time. It is that important. And then I'm going to sort of try to translate it. Maybe in other words, if you don't, and then we're going to like get to it, but I'll say it one more time. The patterns of field line diagrams are only as asymmetric, asymmetric, as the distribution of source charge which creates them. Okay, now I'm going to try to explain that. If you put in the chat, could you say it one more time? I still didn't get it. I will not be insulted or insult you or upset. If you put in the chat, I need to hear that again. I will just think, good, that person's really paying attention. Okay, I will not. I mean, I don't want to. I'm not going to say it again unless someone asks me. But if you ask me, I will not. And you ask it privately, I will not say your name. Like really, I want you to get this. Now I'm going to explain it now. That might help also. And then I'm going to move on. I'm saying, if you look at those field line pictures that we were looking at last week, and if you realize, I mean, and I think they got sort of intricate. They look sort of, the truth is you could draw them if you had to. And if we had more time, you would be able to draw those. But they look like things that you can't draw, really, or they look like things I can't draw. They look like they're getting very fancy. And you notice, hopefully, the field line picture gets fancier and fancier, more and more intricate, more complicated as the situation grows more complicated. What is the situation? The situation is whatever shape or distribution or arrangement of source charge it is that we're picturing to create those field lines. So the more protons and the more electrons you collect, and the more you arrange them in some sort of like fancy arrangement, the more complicated a field line picture they create. And again, remember, this field line picture that we see is just a small slice, a small representation of what's happening everywhere in space due to every time you plop down any amount of protons or electrons, right? So the field line picture gets more complicated as the arrangement gets more complicated, the source arrangement. But what I'm asking you to write down, what I'm trying to drill into you is the converse of that, the sort of opposite. It might seem obvious like everything else we say in physics, but it's not obvious, and it's until you really think it through. And it's not obvious how important it is, or at least it wasn't to me. I'm saying the converse. I'm saying, yeah, as complicated as field line pictures can look, as different, as unpatterned as they can look at first, much as different things can go on in a field line picture, they're only as different, or as the patterns only start changing. There's only as many changes in a field line picture as there are in the shape of the charges that are creating those field lines in the first place. In other words, if you have the simplest possible situation, one dot, 1 point of charge creating field, then you get the simplest possible field picture, a bunch of radial lines just directing space's attention all the way to the source of those radial lines. Like you just get a bunch of radial lines equally in all directions saying wherever we are in space, as long as we're a certain distance, any point in space at a certain distance from that original charge will experience the same type of push or pull with the same strength and in the same direction. But if you're anywhere in space and you trace the line back, you find out what created the line. You find where that one dot is creating all these radial lines. In other words, the simplest possible field line picture will be created by the simplest possible distribution of charge. And therefore, as you make your picture more and more complicated, as you make your source distribution more and more complicated, the field line picture only gets as complicated as it needs to. So what I'm ultimately saying is, and of course, field lines are just our way of picturing what's going on in space. We don't literally think that there are lines in space, but lines are our way of talking about what's happening in space. And the ultimate way that we're talking about it is we're ultimately saying field lines are a difference that make a difference. Field lines over here convey any kind of oddities or existences or field lines over here convey what's happening over here by the amount of asymmetry that characterizes them. The more asymmetry in a pattern of lines there is over here, the less patterned a bunch of lines looks over here. That means that's telling us there's something very unpatterned and very odd or very asymmetric happening over here. And asymmetry means things happening. Remember, in the limiting case, if there was nothing in space, if there was just pure space, we would have pure symmetry. Space, by definition, is sameness. Space is the same in all directions and in all regions of volume. Like any 2 cubic centimeters of space you pluck from any 2 locations cannot be distinguished from each other. All cubic centimeters of space are indistinguishable. All directions of space are indistinguishable from one another. So space is sameness. When I say that field lines over here are conveying the information of stuff inhabiting space over there, what I'm really trying to tell you, and I really will move on, but I'm really trying to tell you that the way field lines convey the presence of particles inhabiting space is that field lines convey asymmetries. The way space registers that something is going on in space is it registers an asymmetry, an asymmetric interruption in the otherwise symmetric state that space would be. So asymmetries in field lines over here indicate the presence of charge or mass over here. It's all about asymmetries. The more asymmetric a field line is, or a set of field lines is, the more asymmetric the original source distribution. I'm saying this way too many times now, I realize. But the flip side of what I really want to get across again is that whenever you sit down to construct a field line picture or imagine what a field line diagram would look like, whenever you're faced with a new situation, a new distribution of charge, and you're trying to think, well, what would the field lines look like? Remember, they'll look as simple, as smooth, and as symmetric as they possibly can, given the shape of whatever is causing them. Okay, that I can't say it any other, just bear that in the back of your mind as we now, and bear in the back of your mind that field lines convey information convey the information. Field lines are the way that space tells space what's going on in space. Field lines are the way that one point in space over here knows what's going on over there. I can't emphasize that enough. Now, I'm going to go to the material that we started at the end of last time. And of course, my board just died. But what we're going to now, if that board up, there it goes. Okay, hang on. Okay. Where we left off, and I'm changing the view on the screen. Yeah, where we left off, top equation up there. That is a definition. That's supposed to be a triple equals sign. what we're defining on the left side is capital Phi E sub E for flux. I'm defining here electrostatic flux. And what flux ultimately is the total amount of electrical field flowing through some kind of area. Flux is stuff through an area. Total flux is total amount of stuff times total area. The stuff that I'm talking about in this case is not really stuff. It's electrical field strength. So if I talk about the total amount of electrical field, if I were to have you picture a wall and I were to talk about the total amount of electric flux through that wall, what I would mean is take every bit of the wall, every little bit of air, take every little bit of the wall, ask in that bit of the wall, like every, say, square centimeter of the wall, ask in that square centimeter, how much field strength is hitting that square centimeter of the wall perpendicular to the square centimeter. Okay, this is where the vector notation comes in. If I were to ask what's the total flux of the total electrostatic flux going through a wall, I'd be asking you to picture a little square centimeter of the wall, ask you to add up the total amount of field strength due to any field lines that are hitting that square centimeter perpendicular to it, or more specifically, if there were a bunch of field lines hitting the square centimeter at some funny angle, I would ask you to just count up the components of the field lines that were perpendicular to the square centimeter of wall. So I would ask you to then to multiply the field strength in newtons per coulomb by the small little area that you just investigated, say 2 square centimeters, right? So say you had like 3 newtons per coulomb of field strength hitting that little bit of area, and you multiply that little, and you multiply it by the little bit of area, say 2 square centimeters. So far you would have like 6 newtons per coulomb times square centimeter, right? You would take that total, that product of field strength, newtons per coulomb, times area, square centimeters. You take that little total and you put it in your bag, or you put it in your head, or you'd write it down on a piece of paper. And then you take the next step to the next square centimeter, the next 2 square centimeter like square, and you'd ask, what is the total amount of field line strength hitting that area perpendicular to it? Maybe this time it's like 5. So you'd multiply 2 times 5, you'd get 10. You'd add that to the 6. You'd put that also in your bag or in your head or on the piece of paper that you're writing down. And you would just keep taking square centimeter steps. I don't know why I made it 2 square centimeters, just so you'd have a number to work with. But you'd keep on taking small square centimeter steps all around. And at each step, asking what the total amount of field strength perpendicular to that step that you make. And you keep on multiplying out field strength by a little bit of area. And you keep on adding up all those field strength times areas. And when you were done with the whole area, and you had counted all the tiles, so to speak, and all the amount of field lines going through the tiles, when you added up the whole thing, that would be called an integral, right? I mean, this is why this is it. So each time you took a step and you only looked at certain vector components and you only looked at field that was hitting the area at a certain angle, that's why you were doing a dot product. That's why the vector symbols are there, the dot product, because we're only looking at we're looking at the scalar product of field coming in at a certain angle relative to area at a certain angle. You would add all of those up, and that's why it's called an integral, right? And you would notice that it's a double integral because each step you're taking is actually a 2-dimensional step. So technically you're integrating with respect to area. If you don't like that idea, if that's uncomfortable, if you're like, wait, when did life become 2-dimensional? Well, I'm taking a 2-dimensional step. What does that mean? I mean, what it means is you're stepping on a tile instead of just taking a little bit of distance, instead of advancing a little bit of linear distance forward, instead of just looking at how much field there is on 1 meter of length, you're looking at how much field there is on 1 square centimeter of area, right? That's what it means. But if you don't like that, you could think of it instead as you just take a bunch of, You just take a step in the X direction, ask what the field is, multiply them together, put in your bag, then take another step in the X direction, ask what the field is, multiply them together, put in your bag, take another, and then when you're all the way done, all the way down the X dimension of all this, then make a right turn and do the same process again, all the way down the Y axis, multiply the two together. And so in effect, you're really doing an integral, a one-dimensional integral multiplied by another one-dimensional integral. So in the end of the day, you have this big two-dimensional integral. That's why it's written as a double integral. I'm just saying in the long run, I'm saying, note that by ds, what I really mean by definition is dx. What I mean by dx is really dx times dy. So this is really an integral times another integral. But anyway, at the end of the day, you would have the total field strength flowing perpendicular out through a certain area. In the end of the day, so I'm going to say this to you and then I'm going to move on. In the end of the day, if you want a simple, maybe these symbols are intimidating to some of us, they still are sort of intimidating to me sometimes. If all the vector symbols and the integral symbols are intimidating, at the end of the day, what I'm saying is electrostatic flux is electrostatic field times area. That's really all I'm saying is it's field times area, but it's an integral because we're taking into account the possibility that the amount of field at each little bit of area might not be the same always. The field might be varying as a function of the field strength might be varying from bit of area to bit of area. So we can't just say field times area because what number field would we use to multiply by area if it's different all the time? So we actually say that it's the continuous sum of a bunch of little field area products. That's okay. So that's why we use the integral. Bottom line, field is stuffed through an area. But then I'm also throwing in this little word out in there. It might even say electrostatic flux. Well, I'm saying out to acknowledge the fact that there can be plus and minus signs. There can be direction. And when we're talking about fields, when we're talking about areas that allow us to distinguish between out and in, when we're talking about a certain kind of area called a closed area, when an area closes in on itself and allows there to be a concept of out and in, as you'll see in a minute, like when we talk about this, like a box, whenever there is a clear concept of out and in, then out we designate as positive, and in we designate as negative. So net flux is always understood to be all the arrows that are going out minus any arrows that might be pointing in. Okay. Yes, exactly. It's like a closed shape. Whenever there's a closed shape, which we're going to deal with like right now, that good direct chat person. Yes. Whenever it's a closed shape, then there's a concept of out and in, outside the shape or inside the shape. And whatever's outside we call positive. All right, now this is all a bit abstract, isn't it? So I'm going to do now an example. I'm going to do a computation for the rest of this period. I'm going to show you all how to compute electrostatic flux in one very fundamental example. I'm about to turn the page. Just let's understand going into this situation. Number one, when I say compute, there's not going to be any numbers here. We're talking about functions. We're talking about mathematical relations in general. So I'm going to show you how to get the total amount of electrostatic flux for a certain situation. The situation is all defined. All the givens and the constants of that situation are going to be letters, not numbers, just so you know. So therefore, two, I'm showing you how to do this partly so you see how flux is computed and you get a better handle on the concept. But also, number three, I'm doing this particular example because the result of this particular example is extremely illuminating and historically important, and the result of the example will actually set us up for the last two classes and show us something we need to know about space. So this is, so again, this is a very important example that I want you to follow. I'm not saying that you're going to be responsible for doing 85 other different exercises like this one. I want you to follow this one. Okay, so here we go. Here's a fundamental application or example of electrostatic flux, how to compute electrostatic flux. And here goes my board again, or maybe not. Let's see. Okay, so here's the example, the situation. Let me change one thing. Okay. Here's I'm going to draw a picture on the next page, but here, given some point source of positive charge plus Q, right? So we have like a proton sitting in the middle of the lab, or really, like 16 quintillion protons jammed together in a tiny space. There goes the board. It was bound to happen. But imagine you have some proton or some amount of protons that has some positive, and they're all like squeezed together into a little point. So we have some amount of positive charge located on a point, and the positive charge is known as plus Q. Then I'm going to ask you to imagine, I'm going to put the board back up in 1 second, but I'm going to ask you to imagine a spherical shell surrounding that charge, centered on that charge, and having radius lowercase r. So imagine, so the charge is like real in our minds. It's like sitting there in the lab. We're picturing a proton sitting in the lab, or a proton sitting way out in deep space or something. And then we're picturing a region around it. We're picturing some spherical shell, some sphere, but just the outer rim of the sphere surrounding that charge, centered on it, a radius Q. And what we're going to calculate is the total amount of flux through the spherical shell surrounding this charge. Okay, so let me put the board back. Okay, here it comes. Okay. Okay. So again, so the words are: given a spherical shell of radius r centered on point source positive Q, compute the net efflux, the net electrostatic flux through the given spherical surface area. That's the question. So in other words, and again, you can tell me to go back if you want, but here's what I'm talking about on the next page. So we have point plus Q at the center, like in blue, right? Then, and ignore the red lines for a second. I mean, I think you know what they are, but just ignore the red lines for a moment. Notice that there's a dotted brown line circling around the blue dot. The dashed brown line is a circle, at radius r. We could say lowercase r. And it's meant to be a cross section. Like, I only have two-dimensional page here to work with. This is all meant to be a cross section of something that's happening three-dimensionally. So this is supposed to be like a sphere that's surrounding plus Q in our mind. There's no material, like the Q is real. And the field that the Q creates is real. Like, it's abstract, it's not material, but it's real. Like, we believe that charges create fields in space. So I've drawn the field lines, the field line diagram caused by this Q. The field, remember, those red arrows, those red lines are field lines. And remember, the whole idea of field is they exist the minute Q exists, then they exist in space. And those are just 8 representative lines that are showing the pattern of field lines that are actually going on forever, everywhere in space. And they are there the minute Q is there, whether or not there's any other charges in space, and whether or not I imagine some sphere or even put a sphere actually there, right? So that's real. Like the solid blue and the solid red are real things happening in space, even if they're not easy to see or something like that. They're real. But then the dashed brown thing is what I'm picturing. I'm picturing an area, a surface area in a spherical shape surrounding the Q. Now it's an area, right? You might call it a surface. It's an area, even though it is bent or warped or curved into the third dimension, just like the surface area of Earth is an area, right? It's bent, but it's a surface area. It's the outer border, the outer boundary, or the outer skin of a three-dimensional sphere that's enclosed within it. But the surface area of the Earth is an area, right? It's measured in square meters, not cubic meters nor meters, square meters, right? Now, this is an example right here. Before I go any further, this surface area that I'm imagining, this shell, this round shell, like the skin of a grapefruit or something, that I'm imagining to surround, to enclose the point source Q, it's an example of what we call a closed area. It is an area, but it's been bent so that it touches itself and it closes in on itself. It encloses an interior, right? There's definitely like some areas are flat. Some areas are like the area of your desk. That's called an open area. It is an area, but it's not wrapped around touching itself. In fact, let me back up really quick. Do I have time to do this? To give a more concrete example, we can say all this kind of terminology in the context of one dimensions. Here is a length. The length of this stylus, right, is a one-dimensional length. It's from one end to the other is measured in meters. It's a one-dimensional length. But I could, well, if this were a string, I could bend it and touch the ends to themselves, and I would still have a length. The string would still be the same length. It would still be 5 centimeters long. Only now that I've bent it, now that I've bent it into 2 dimensions and touched the ends to itself, it's what we would call a closed length or a closed path. It's still a path. Its size is still measured in one-dimensional units. Only now, the kind of path that it is, you might call a perimeter or a circumference, right? A one-dimensional length can be open or it can be closed. And once it's closed, it encloses an interior area, right? Like if you make a ring out of a bunch of metal, then there's a flat disc bounded by that ring that we call the area inside the ring. And then there's all this area outside the ring. There's no inside and outside when you have an open length, but once you close a length, there's outside the length and there's that which is enclosed within the length. Same thing with areas. You can bend an area so that it is a surface area, so that it's 2 dimensions, but closed in on itself, and it will enclose a region within, a volume within. And so all these field lines, so that's the kind of situation we have here. And these field lines that are there, no matter what, that are just there from the charge, they're all flowing out of the closed area. So our job is now to compute the total amount of field strength busting out of that particular area, that closed area that we're picturing, that we're considering. That's what we're going to compute, the total flux through that area, understanding that remember, flux is always just field lines through an area. Just we're starting right in with looking at the flux through a certain type of area that is a closed area. It makes things a little bit more interesting and important. I'm going to pause. Can we look at the time? Yeah, all right, so we got that. So we're going to do the computation. I know I'm talking about this a lot. Hello, I mean, have we met? Of course I'm talking about it a lot, but I'm also, because it's a little bit abstract. It's a little bit, I mean, it definitely intimidated me the first time I saw, I don't know. But we're talking about flux now. We were already talking about field for the last couple of weeks. That's already abstract enough. Now we're going another level and talking about flux. Like, but what's the deal? Like, I'm going to try to compute the total amount of flux through this surface. You might well ask, like, what does that even mean? Like, why would you care? And what if you get an answer, Yaverbaum, and your answer won't even be in numbers, it'll be in letters. What does your answer like even indicate? Like well, one quick version of this is is, remember, field by itself is a concept that applies at one point at a time in space, much like force. Back in the day in physics 203, remember, we had this whole concept of force, and we ultimately we would look at all the forces acting on an object, and we would draw a free body diagram. And our whole idea in physics 203 was that if you look at any one point of mass at one point in space, at one point in time, you investigate or you draw all the arrows, all the vector arrows representing all the pushes and pulls acting on that point of mass at a given point in space and time. If you add together the vectors representing all the forces acting on one point in space and time, then our belief was F net equals ma. Our belief was that you would know the instantaneous acceleration. You would know the second derivative of position with respect to time at that point in space and time. And from that snapshot, we felt we could predict what was going to happen later to the point of mass, like what velocity it would have later, and therefore what position it would be at later. Or we could retro it and look at what happened before. So our whole idea with forces and accelerations was we were taking these snapshots of points in space and time, and from the snapshots inferring larger movies of movement, of position, velocity, and acceleration. It was a one point at a time kind of way of looking at the world. Very, very powerful, but eventually gets limited and eventually gets very, very cumbersome. So we then said, wait, couldn't we ever, I'm going back to physics 203 now. I'm saying we had a picture of forces and accelerations, and that was all a derivative picture. It was all about derivatives. Infinitesimal regions of space and time. But eventually we said, couldn't we back up and zoom out? Can't we look at what force is doing as it acts through a bunch of points? What about when something pushes or pulls some mass throughout a whole displacement? What about pushes that are acting throughout continuous intervals, but continuous finite intervals of space? We said a push or a pull acting throughout a displacement from here to there was called work. And we said work transfers energy. And we eventually developed these theorems called energy conservation and related theorems that allowed us to look at the impact. The ultimate point of work and energy was a way of allowing us to look at the accumulated impact of force acting throughout a finite, measurable region of space. Work and energy allowed us to elevate our perspective from just going one point at a time, from going from infinitesimal regions of space to actually looking at finite, continuous, measurable regions of space. That's why we moved in our way of thinking from forces to work and energy. Same thing here. We're thinking about fields now. We're never going to get rid of fields. We love fields. Fields are our focus now. But fields act on one, field lines, field vectors, whatever, act on one point of space at a time. What we're going to do now is look at what's the accumulated effect or impact of the field throughout this entire measurable, finite, continuous region of space. To go from field to flux in our consideration is like going from force to work. In fact, it's not a coincidence that force is an integral of a dot product and flux is an integral of a dot product. It's the same type of reasoning. So we're going to calculate, I know I'm yelling and screaming. We're going to calculate the net electrostatic flux through this area so that we can see the accumulated effect of field acting throughout this entire measurable finite region of space, this region that happens to be a spherical shell. last way to put why we're doing this or what we're doing, it's like if you had a light bulb in the middle of the room and the light bulb shines light in all directions of three-dimensional space. One of the most direct, most common ways to start seeing the effect of that light, the interplay of that light on objects in the room versus that light on non-objects in the room. In other words, to see the interplay of light and shadow, one of the easiest ways is we pop up a screen, right? We look at a screen and we let the light from various objects in the room bounce on the screen, and we let the light that doesn't hit objects in the room not hit the screen. So then we get patches of brightness and shadow on the screen. So we use the screen as a two-dimensional slice by virtue on which we can project the impact of the light that is spreading throughout three-dimensional space. That is what we're doing here. Because when we investigate flux, we're looking at a two-dimensional slice of space and looking at the accumulated effect of the field on that two-dimensional slice. Just bear in mind that slices don't have to be open, they can be closed, and that's the type of slice we're looking at here, a closed area known as a spherical shell. So we're going to compute the total flux through that spherical shell. So here we go. We first write down the definition. Flux, by definition, equals double integral of field with respect to surface or area. Again, please remember ds. ds is the variable of integration. ds, the s stands for like surface. So ds is a little bit of surface or a little bit of area, or in this case, a little bit of surface area. Okay, so we're going to we have to integrate that function. That looks a little intimidating, maybe. Let's first remember that whenever we say field, we mean a function. Field is always a function of r. It's a vector valued function. You plug in as the input the r displacement from some source charge. In other words, you plug in the position in space in which we're interested. And then what the function pops out is the magnitude and direction of the newtons per coulomb vector waiting to happen at that point in space. So field is always a function. The more complicated the distribution of charge creating that function, the more complicated the function. We don't know all the field functions for all the different complicated possibilities in the world. In fact, that's ultimately what we're here to compute. But we know one. We know the field function for the fundamental, elemental, simple case of one point source. That happens to be the case that we have here. We know the field function created by a point. It is given by Coulomb's law. It's given by Coulomb's law, which it says here. Coulomb's law says that the field vector over here at R created by a point source over here, Q, is that complicated constant, but it's just a constant, that constant times the magnitude of charge divided by the square of the distance between the source charge and the field point. In other words, wait, so what I'm saying is this. Right, remember, this law, Coulomb's law, assumes that there's a point charge over here, and we're investigating a point in space over here. So we draw in our mind a displacement vector called r that points from the original charge to the location in space. The vector r is a simple product of its pure magnitude, its pure distance, lowercase r, times its pure direction, r hat. R hat is a vector that points in the same direction as r, but only has length 1. It's the unit vector, right? R hat is the unit vector that points in the direction of r, i.e. it points from the original charge to the landing spot, the location of interest, right? So the law, Coulomb's law, tells us that that's the field function from a point source. So that's what I'm going to plug into the integral. That's what I have to integrate with respect to ds. So here I go. I plugged it in. Why is top of the board cut off? I don't know. I don't know why Oh, it's not. Okay. So the field function is plugged into the integral. So we're integrating 1 over q over r squared r hat dot ds. Now that looks a little complicated. Let's deal with the vector part first. The vector part is certainly intimidating. Excuse me. Okay. Let's deal with that first. Remember, first of all, for any two vectors, that says for any two vectors, A and B, the dot product of the two vectors, A dot B, A vector dot B vector, is by definition the magnitude of one times the magnitude of the other times the cosine of the angle between them, right? The whole idea of the dot product, again, it's the scalar product of two vectors. It measures not only how big they are, but how parallel they are to each other, right? The more, remember the cosine of 0, you might want to write this down if you do. Well, remember the sine of 0 is 0 and the sine of 90 is 1. Therefore, the cosine of 0 is not 0, it's 1. And the cosine of 90 is 0. So the smaller the angle between two vectors, the more close they are to parallel, the bigger the cosine, the bigger the dot product. If two vectors are purely parallel with each other, the dot product is simply the product of their two magnitudes. And if two vectors are purely perpendicular to each other, then their dot product is 0. Right? Because the cosine of 0 is 1. So the dot product is meant to only count, is the dot product returns a product that ultimately is scaled. Okay, I'm making this more complicated. The dot product is bigger. The dot product between two vectors is bigger and bigger if the two vectors are parallel to each other, and it's 0 if they're perpendicular to each other. Okay, so what are these two vectors? Well, vector r, the two vectors that we're dotting are r hat, right, and ds. Well, what's going on with that? Well, r hat, we just said a second ago, r hat is the unit vector for r. It points in the same direction as r. R hat, in other words, r hat is a unit vector. It has length of 1 by definition, but it has a direction that points from Q to whatever little bit of area we're looking at on the surface. R points, in other words, along a radial line. That's how R points. So R hat is a direction is a vector in a radial direction and with a length of 1. ds, okay, ds is a given bit of infinitesimal area. Now what does that mean? What? It's hard to draw. Well, actually, that's a bad draw. Hold on a second. Okay, that's better. Area is not a vector. Area is a two-dimensional space, whose size is measured in square centimeters. But areas have orientation, right? And our whole concern with flux is we want to be able to track. We only want to count up and care about field lines that hit our areas at a certain angle. So we care about the angle of our areas. So the way we track the orientation of areas is we imagine a little vector sticking out of it. We imagine a little arrow like taped to the area, sticking out of it, perpendicular to it, pointing along a normal line, as it says down here at the bottom of the page. ds, the vector that is stuck to a little bit of area, points along its norm, along a line normal to the area, a line perpendicular. And the whole idea is, and the bigger the area, the longer the arrow. So the whole idea is we've got this little flag sticking on the area. And as you rotate the area, the flag rotates by the exact same amount. So the flag, the vector, is a way of being able to keep track of the orientation of this area and keep track of the extent to which the orientation of this area does or does not match up with the orientation of other things, such as other arrows. So whenever we talk about area, we could talk about it like it's a vector. We could talk about it like it has direction. But the way to talk about the direction of an area, if you picture this picture that I just gave you, the direction of an area is really the direction of an arrow that already sticks perpendicular to it. So, right, because that's the easiest way just to picture it. So, in this situation, if you think about it, if we're walking around all of the bits of area around this surface area, this sphere that's surrounding the point charge, wherever we are, and this is the part I want you to picture, even if you don't like all this vector stuff, just picture this for a second. If you're walking around the surface of the earth, no matter where you stand on the surface of the earth, okay, if you picture a flag just sticking out of the surface, a flag that represents the norm to that surface, if you picture a vector that's indicating the orientation of that surface, no matter where you stand on the surface of the earth, that flag that's sticking out of the surface, it will always be directly, necessarily, purely, fully parallel to a radius that would come out of, that would be drawn from the center of the earth up to wherever you're standing, right? In other words, the area of the surface of a sphere is always purely perpendicular to all the radii of that sphere. Radii hit the sphere, the surface of the sphere, perpendicular to the surface of the sphere, right? I mean, all my verbiage, I'm just trying to say that all the radii of a sphere hit the surface of the sphere perpendicular to the surface. Therefore, all the field lines coming out from the center of a sphere would hit the surface of the sphere perpendicular to it, because all the because all the field lines are radial. So I'm saying all of that is to say that if we're doing this math and we're trying to do this intimidating looking integral bit by bit, if we're first looking at the vector notation, r hat dot ds vector actually equals, like by definition, the magnitude of r, which is 1, times the magnitude of ds vector, which is ds, whatever that is, times the cosine of the angle between them. And the angle between them is necessarily 0 everywhere, because all of these r's are radial and all of these ds's are radial. So the angle between them is, no matter where you're standing, is 0. So the cosine is necessarily 1. So that complicated bit in the integral, the r hat dot ds vector, just ends up equaling 1 ds. So I'm just going to substitute ds back into the integral. So I've just dealt with the vector part of the integral is what I'm saying. Now, I'm not saying it's always that easy in all integrals. The vectors are there for a reason. They're there to force us to keep track of direction and directional relations. But here in this case of a sphere surrounding a point, all the field lines end up fluxing 100% perpendicular through the surface. So we don't have to take complicated components. The flux is as simple as we would like in terms of directions. That's why we picked a sphere. That's why we picked this example, so things would simplify. So we get 1 ds in the integral. So now we don't have to worry about vectors anymore. We've dealt with them. So now we have double integral of 1 over 4 pi epsilon naught times q over r squared ds. And that still looks like quite a mouthful, doesn't it? So let's deal with it on the next page. I just recopied it at the top. So there's no vector symbols anymore. Again, we're not ignoring the vector symbols. We just dealt with them. We went with them. We used the definition of dot product to do the dot product. And now the vector symbols are gone. And there's nothing. Okay. So now we've got this double integral. Now notice the variable of integration here is ds. That means an infinitesimal bit of surface, of area. That's what's varying is whether we're standing here at this little ds and counting up the field lines there, or whether we're stepping over here to this little bit of ds and counting up the field lines there. That's what's varying, ds. Which little bit of ds are we looking at? And what's making it an integral is that we're imagining us ultimately standing on every single little bit of area on this surface and adding them all up. But we're picking every single ds at the surface of a sphere that we imagine having a given radius called lowercase r. So what I'm emphasizing right now is ds varies from place to place given a certain fixed distance r from the center. Okay, so ds is the variable of integration, not r. So you know from your experience with integrals, anything that doesn't vary, anything that is constant with respect to the integration variable comes out of the integral, right? In other words, well, I wrote this more quickly than I should have. I should have written it in 2 steps. But I'm saying, first of all, we could take the q and the 4 and the pi and the epsilon naught. We could take all of that outside the integral because they're all constants, right? I mean, 4 is obviously a constant. Nothing's obvious, but 4 is a constant. Pi is a constant. Q is a constant. It's not constant from one situation to the next, but in this situation, there is a certain given fixed amount of charge called Q. It stands for just some number. It's like 1 proton or 6, whatever. So it's constant. But then what I want you to recognize is that r squared, that sure looks like a variable. R squared looks like a variable, and in some broader sense, it is, but it's not varying in this context. It's not varying with respect to S. That is to say, R means how far away we are from the point source. Now, we could vary that if we wanted to. We could go farther or closer to the point source. But in this flux integral that we are computing here, the flux integral is asking us to integrate with respect to area. It's asking us to picture ourselves walking all around the surface of a globe, but always at the same surface. So we're not changing R with respect to ds. Are we changing anything? Yes. We're sometimes standing here and we're sometimes standing there and we're sometimes standing there on the surface of this globe. But so we're changing ds. But no matter what ds we pick, it's always at the same r. So r is a constant with respect to ds. So it comes out of the integral. So now we just have the integral of a bunch. So this is getting a lot simpler, right? And that's why we looked at that. This is why we care about flux. We care about flux in situation. Flux is an intimidating looking integral that is designed to help us investigate situations where, in fact, if we understand what integration means well enough, this is why we focused on it so much at the beginning of the semester. If we actually understand what integration means and when it is used, the purpose of these integrations that we're doing in these last few classes is they're set up so that hard integration doesn't actually have to be done. We don't have to compute anything difficult here. We see that if we understand how integrals work. All of those letters come out as constants of the integral. So we're just left with the integral of ds. Now, what the heck is that? Well, what's the integral of x? Excuse me, what's the integral of dx? It's x, right? What's the continuous sum of a bunch of little bits of length? It's total length by definition of the integral. So same thing here. Hello. Same thing here. Well, here's what I'm saying. By definition, there goes the board again. But by definition, the integral of dx, yep, Lordy. Boom. Thank you. So by definition, the integral of dx is total x. So if dx was a little infinitesimal bit of path, then the integral of dx, add up all the little bits of path, get total path. Similarly, integral of ds means add up all the little bits of surface area, get total surface area. Right? That's what it means. So we mean the total surface area of a sphere. We've got 9 minutes. Is this one? The total surface area of a sphere, if you recall from geometry, the total surface area of a sphere is of radius r is 4 pi r squared. Okay, so if we plug in, oh, there it goes again. Come on. Okay. So if we plug in, so all we have here in this calculation, it seems, is this flux calculation we're doing is field times area. Now, let me back up again in a second. In a way, I'm saying I just walked you through all of this subtleties and nuances of like integration in order to arrive at something comparatively simple. Like, remember at the beginning of the class, I said, look, really at base level, flux just means, electrostatic flux just means field times area. We only have to deal with all this integration stuff if the field amount is changing from bit of area to bit of area. Well, after we just went through this whole discussion, we find this is one of those examples actually where it might not seem at first, but if you look at it, since we picked a surface area, since we picked a spherical surface area surrounding a point and centered on that point, what I'm really saying in English at the end of the day is wherever you walk on the surface area of that sphere, wherever you walk, you find field lines hitting you at 90 degrees, and you find the same number of field lines that you find anywhere else you walk, right? The field lines are equally dense at this place on the sphere as they are over here on this place on the sphere. And they're always at the same angle. So the magnitude and the direction of the field lines everywhere at the surface of a sphere centered at a point, the magnitude and the direction are constant. So in fact, after all of this mishigas, all I'm really saying is if you want to do the flux integral in this example, you ultimately find the whole expression for E really comes out of the integral. And you're really just saying, fine, what's the total? What's the E times the total surface area? And the total surface area for this sphere is 4 pi r squared. So then we say, oh, well, that's interesting because if you look on the page, that means the 4 pi's cancel and the r squared cancel. What we find as a result for this whole thing is that the total flux, the net electrostatic flux out of the surface of a sphere centered on a point source, the total flux is just the amount of that point source Q divided by a constant. That's it. A bunch of stuff canceled out. Specifically, the R's canceled out. Now, this means something. This is one of the reasons we're focusing on a sphere surrounding a point. It's saying flux, the total impact of the field. If we add up what the field is doing everywhere on this whole sphere, we get a number, Q. And remember, this is a number, right? Q stands for some number. It's like 1 proton or it's 16 quintillion protons or something. But whatever it is, it's a fixed number. And E is a fixed universal constant, 8.85 times 10 to the negative 12 farads per meter, whatever. So this is a number. And this number that we're getting doesn't seem to depend on R. What we seem to be saying is, if you have a point charge right here and you imagine some sphere surrounding it and you want to know what's the total impact, the total accumulation of field throughout the entire surface of the sphere that you imagine, apparently it doesn't matter how big that sphere is. Whether the sphere is big or small, you get the same answer. And the answer depends, it doesn't depend on the size of the sphere. It seems to depend only on the size of the charge that the sphere enclosed and centered. Now, right, so what we're saying is for a spherical shell centered on a point source, the net flux is independent of shell size. As long as the shell is spherical, the R cancels out. Now, why is that? Right? But that's what we're finding, and that's a big deal, actually. Why is that? Well, mathematically, because the R's canceled out. But why did the R's cancel out? Because the surface area of a sphere is directly proportional to R squared, and the field due to a point charge is inversely proportional to R squared. So if you pick a sphere and calculate the flux, you get an answer. If you now pick a sphere, if you double the R and you pick a sphere that has twice the radius as before, then the size of the area of the sphere will now quadruple, right? I mean, if the radius multiplies by 2, then the area will multiply by 4. So now you're adding up an area that's 4 times as big as before. But everywhere you go to put in, everywhere you look on that area and look at how much field strength you find field strength that's 1/4 as strong as it was at the smaller sphere. The sphere gets bigger at the exact same rate that field gets weaker. That's right. And in fact, that's a major insight, as that's not a coincidence. That's why fundamental forces fields like gravitational field, the electrostatic field, when you first write them down, it's like blah, 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 over R squared. Certainly to me, when I first saw that, I was like, over R squared, where's that coming from? That's like so obscure, divided by R squared. But it turns out it's not random. The point is, field gets weaker and weaker as it spreads out, because it spreads out equally in all directions, creating a sphere of influence. Its influence weakens at the same rate that the sphere of influence broadens. Field spreads uniformly, equally, and constantly like a sphere. But an even deeper insight about this, and we're almost done. We've got 3 minutes, and there's an even deeper reason this is happening that's so deep that this is where we're going to end. It turns out what we just found for this extraordinarily contrived simple case of like one dot with a sphere around it, we just found that in the case of a sphere enclosing one dot, we found that the flux through the sphere does not depend on the size of the sphere. But it turns out that we can generalize that. That's even a bigger conclusion than it looks like. Because if you think about it, flux means field strength multiplied by area. Fine. But how do we express field strength when it comes to diagrams? We express field strength with field lines, and the number of lines per unit area is how we indicate or represent or compute field strength. So flux is field times area, but field is number of lines per area. So flux is number of lines per area times area. In other words, flux really, if you're asking way at the beginning of this whole class, like, oh my God, we're going to talk about flux now. Like, why is he calculating flux? He's going to calculate the number of flux through a surface area. What does that even mean? And if you really think about it, at the end of the day, to compute why flux is so useful, to compute the total flux through a region of space is really just to count up the number of lines, literally to count up the number of lines through that region of space. Flux means number of lines per area times area. That means number of lines, period. So what we just found here was that if you take a point charge and it creates field and you surround it with a sphere, it doesn't matter how big the sphere is, you're going to get the same flux, because really what we're saying is, oh yeah, like if you just count up the lines that some point creates, it's the same number of lines, whether you capture them in a globe this size or a globe this size. Field lines are like matter. Even though they're information, they're like matter. They don't get created or destroyed spontaneously in space. Whatever field lines start, the only field lines you're ever going to capture out here are field lines that started at a charge. So the number, so I know it's 420, so I'm just going to say this and then done. What I'm saying is, even in the simple example led us to realize, like, oh, if I count up 8 lines coming out of one point charge, then I don't care how big my sphere is that I surround the charge, I'm going to have 8 lines busting through that sphere, no matter how big, because as the sphere gets bigger, I get a bigger sphere, but the lines get more spread out. Lines always act that way. So from here on in, it is a law, and I'm ending with this. It's a law that whenever you compute the flux, the net electrostatic flux out of any closed surface, any surface that can be regarded as a container, the total amount of electrostatic flux busting out of any container anywhere in space is 100% determined by the amount of charge enclosed by that container. Whatever charge is inside will totally determine the amount of flux going through the container, regardless of the size or shape of the container, regardless of the size regardless of the shape of the charge within, and regardless of any charge that might be outside. This is called Gauss's law. It says that the net electrostatic flux through any closed surface is always fully determined by the magnitude of charge enclosed by that surface. That is it. I held you over 2 minutes or 1 minute. I apologize. We'll talk more on Wednesday. You've been but yes, have a great day. Thank you all.
Have a good day, Professor.
Thank you, Savannah. No green square.
Have a good day, Professor.
Thank you, person that I didn't see that green square, but I think it was sorry, but yes, you too. Thank you guys. Great job. I owe you my life, or at least document. Yes, have a great day. Thank you. You too. I'm going to change it. Awesome. Great. Good question at the beginning, Rashman. Great question. Are you still there? Okay, wait. I'm going to. So are you still there? Do you need, well, I'm going to turn off are you copying down notes, or should I? Okay, well, I'm closing the recording, going once, going twice. Goodbye to the recording.